Good morning. Welcome to the continuation of tutorial number 10. We will continue with problem number 5. A rigid vessel initially contains 2 kilomole of carbon and 2 kilomole of oxygen at 25 degrees. The carbon is in solid state. The pressure is 200 kilopascals. The combustion occurs when the ignition is onset. The combustion occurs, and the resulting products consists of 1 kilomole of carbon dioxide, 1 kilomole of carbon monoxide, and whatever be the excess oxygen that also remains in the product. And the products leave at a temperature of 1000 Kelvin. Determine the heat transfer to the surroundings. So, we will work out the solution. The C is in solid phase. Okay, so we will write the expression 2C, 2 kilomole plus 2 O2 giving, they are given the product composition also, 1 kilomole of CO2 plus 1 kilomole of CO. By carbon balance it is done. So, 2 carbon is converted into 1 kilomole of CO2 and 1 kilomole of CO. So, now by oxygen balance, the remaining oxygen 0.5 kilomoles will appear in the products. So, this is the reaction. Okay. So, now please understand that is a rigid vessel, that means constant volume. So, combustion occurs in a constant volume process. So, let us apply the first law, Q minus W equal to delta U. Now, this is PdV work, no other forms of work is there. So, I can say W equal to 0. So, this will be equal to the Q will be equal to UP minus UR, that is the internal energy of the products minus internal energy of the reactants in the final state and initial state. So, we can write this as HP minus P pressure of the products, whatever be the pressure, I will say final pressure also, you can say pressure at the state 2 into V minus HR, the enthalpy reactants minus pressure of the reactants, okay, or initial pressure into V. V is the volume of the reactor. So, now by equation of state I can write this as Hp minus P to V can be written as number of moles of the products into universal gas constant into temperature of the products, which is given as 1000 Kelvin minus HR minus number of moles of the reactants universal gas constant into temperature of the reactants, which is 25 degrees or 290 Kelvin. So, now we have to, so what is HP? HP will be equal to H of, from the reaction I can write the standard 1 into 1 moles of CO2, 1 into H of CO2 at 1000 Kelvin plus, because enthalpy does not depend on pressure. Why? Because for we are assuming that this will be ideal gas. So, for ideal gases, internal energy and enthalpy will be functions of temperature alone. So, I can write this. Similarly, this will be 1 into CO at 1000 Kelvin plus 0.5 into H of O2 at 1000 Kelvin. So, now you know that this is standard enthalpy, which can be written as the enthalpy of formation. So, I will say 1 into enthalpy of formation of CO2 plus the sensible enthalpy, where the temperature is increased from 298 Kelvin to 1000 Kelvin for CO2 plus 1 times enthalpy of formation of CO plus sensible enthalpy of CO at 1000 plus 0.5 times enthalpy of formation of O2 is 0. So, we can just say delta H of O2 at 1000. So, this is the enthalpy of products. So, now to fetch the values we have to go to the tables. I will show you a typical table for CO2. CO2, if you see enthalpy of formation, this is a typical table. You can also use the NIST database. So, enthalpy formation is given here. You can take minus 393,546 kilojoule per kilomole. Similarly, at 1000 Kelvin, delta H, that is H at a particular temperature minus H of enthalpy formation, that is given for CO2. Here you can take from this here 33,425. So, similarly, we can fetch the values for CO and O2. Okay. So, what I can write here is equal to 1 times minus 393,546, which is enthalpy formation, plus 33,425 plus for CO enthalpy formation is minus 110,541 plus sensible enthalpy at 1000 is 21,697. Okay, plus 0.5 times the sensible enthalpy is 22,721 for oxygen at 1000. So, from this I will get the value of HP. Okay, now UP is HP minus NP RU into TP. Okay, so now what is NP? Number of mole of products. Number of moles, that is you counted 1 plus 1 plus 0.5 equal to 2.5 kilomoles. RU, universal gas constant, is 8314 kilojoule per kilomole Kelvin. So, you know that temperature Tp is also given as 1000 Kelvin. So, you know this, so you can find the enthalpy of internal energy of the products, that is UP will be equal to minus 458,389.5 kilojoules. Similarly, I will take now UR equal to HR minus NR RU TR. So, now HR, what is HR? HR is 0. Why? You see the reaction, C is in solid state element and temperature is only 25 degrees, that is 298 Kelvin reference temperature. So, when enthalpy of formation, the reactant side solid carbon is present and the element naturally occurring element O2 is present. So, the enthalpy formation is 0. So, we can say HR equal to 0. So, that means UR will be equal to, so again I have to calculate NR, number of kilomoles of this. So, now if you see the reactant side, this is solid state. So, the kilomoles cannot be counted for the solid states. So, the reactant number of moles will be just the number of kilomoles for the oxygen. So, this will be 2 and the TR equal to 298, RU equal to 8314 joule per kilomole Kelvin. The previous page also will be joule, not kilojoule. Okay, so now substituting this, I will get UR will be equal to minus 4955.144 kilojoule. So, that is the internal energy of the reactants. I know internal products also. Now, what is Q during the process? I can say it is UP minus UR, which will be equal to minus 434.356 kilojoules. So, now heat transfer to the surroundings. This is the heat interaction, this is negative, that means from the vessel where the combustion occurs to the surroundings, the heat transfer occurs. So, heat transferred to the surroundings will be equal to positive of this 453,434.356 kilojoules. Okay. So, please understand the constant volume process, the heat transfer will be equal to the change in the internal energy, but change in internal energy is calculated in terms of enthalpy. That is, the definition of enthalpy is U plus PV. So, using that, U is calculated as H minus PV. And enthalpy, the standard enthalpy of formation and the sensible enthalpy will be taken from the books or tables. Okay, so that is about the problem number 5. Problem number 6. Liquid N-dodecane, the state alkane C12H26, and the standard enthalpy formation of the liquid fuel is given as minus 351 megajoules per kilomole. Okay, now this is sprayed into a combustion chamber. So, steadily enters the combustion chamber of a gas turbine engine at standard reference temperature of 25 degrees or 290 Kelvin and undergoes complete combustion with air. Air that enters at a higher temperature, 700 Kelvin. Now, heat losses from the combustion chamber can be neglected. Okay, say for example, I will say this is the combustion chamber. The fuel is sprayed here, C12H26, that is 290 Kelvin, and air is sprayed here or enters here at 700 Kelvin, and this is insulated, and the products go out. If the temperature of the product should be, I will say products, 1700 Kelvin. I want to maintain the temperature of the products not more than 1700 Kelvin. Okay. Determine the air fuel ratio. So, I don't know the mass flow rate of this. So, let us say 1 kilomole of fuel is flowing. That means A kilomoles or A 4.76 times A kilomole of air is flowing. So, what is this A? That is what we want to find. If the temperature is restricted to 1700 Kelvin. So, we have to find the air fuel ratio, that is the actual air fuel ratio. Now, data is given in this problem itself. The values of enthalpy of formation of CO2, H2O are given here in megajoules per kilomole. Okay, then the sensible enthalpy of 1700 is also given, 73.48 and 57.76 megajoules per kilomole for CO2 and H2O. Sensible enthalpy of oxygen and nitrogen at 700 Kelvin, because reactant enters at that temperature, is given as 12.59 and 12.01 megajoule per kilomole. Sensible enthalpy at 1700 Kelvin is for oxygen it is 47.81 and for nitrogen it is 45.31. So, all the data is given in the problem itself. So, now the reaction we will write C12H26 1 kilomole we have assumed. So, that is the convention to write the thing, A times O2 plus 3.76 times N2, that is the reactant side. Products, complete combustion is assumed here. So, we will say 12 atoms of C is there. So, 12 times CO2 plus 13 times H2O, okay, plus some excess oxygen has to be supplied, correct, or else temperature will not be restricted. So, that means whatever A you put here, when stoichiometric air is supplied, the A is calculated as 12 plus 26 by 4. Now, this has to be higher. So, what we can say, for stoichiometric, A stoichiometric will be for any hydrocarbon like CX, HY, it is X plus Y by 4. So, now for this case it is 12 plus 26 by 4, that will be 18.5. So, 18.5 is stoichiometric, but A is more than that. So, whatever be the remaining oxygen number of moles, that is A minus 18.5 of oxygen will remain in the product, plus 3.76 times A nitrogen also will be in the products. So, this will be the reaction. Okay. So, that means we are assuming complete combustion will take place, obviously because the temperature is restricted to 1700. So, dissociation of products cannot occur. Second one is excess oxygen is supplied, so that CO2 is converted to CO is converted to CO2 and H2 is converted into H2O. So, excess oxygen remains. This 18.5 is nothing but the A stoichiometric, that is, when stoichiometric air is supplied, I have to supply 18.5 kilomoles of oxygen per kilomole of fuel. So, A is more than that. So, whatever is remaining is A minus, that is, this A stoichiometric will be used here. Okay. So, 12 plus 6.5, 18.5, that will remain in the products, but the excess oxygen will remain as oxygen only, nitrogen also will remain as inert. This is a reaction, actual reaction. So, I have to find the value of A if the temperature has to be 1700. So, that means if I write the first law, now the flow process we can assume that the pressure is constant pressure. So, I can say Q minus W equal to delta U, or this is nothing but P dV work, P delta V work. So, we can write Q will be equal to delta H equal to the enthalpy of products minus the enthalpy of reactants. Do you understand? So now please see that the Q is 0 in this case, and there is no heat loss. So, Q is 0. That means I can say HP, the enthalpy of products calculated at 1700 Kelvin, should be equal to the enthalpy of the reactants which are coming in at 25 or 298 Kelvin. So, this is the equation. From this I have to find the value of A. Do you understand? So, the enthalpy products at 1700 Kelvin will be equal to enthalpy reactant at 298 Kelvin. So, let us find them. So, here enthalpy of reactants will be equal to enthalpy of 1 times enthalpy of formation of dodecane plus no sensible enthalpy for this, correct, because it is coming at 298. So, that is the value here, plus A times A I do not know, correct, A times oxygen. Oxygen is coming at 700 degrees centigrade, 700 Kelvin. So, the sensible enthalpy formation may be 0. So, sensible enthalpy of oxygen we have to write. So, let us say for oxygen 0 is sensible enthalpy formation, plus sensible enthalpy is given in the problem as 12.59 megajoules. Everything will keep in megajoules. I will write first the variable to delta H of O2 at 700 plus 3.76 times 0 plus delta H of N2 at 700. So, this is the enthalpy of the reactants. So, this will be equal to minus 351, it is given megajoule per kilomole, plus A times, I will substitute the values, A times 12.59 plus 3.76 into 12.01. So, this is the equation. So, we can write this as minus 351 plus 57.7476 times A. So, that is the enthalpy of the reactant. Now, enthalpy of products. Enthalpy of the products will be equal to 12 kilomoles of CO2. So, 12 into enthalpy of formation of CO2 plus sensible enthalpy of CO2 at 1700 Kelvin, okay, plus 13 times enthalpy of formation of H2O plus sensible enthalpy of H2O at 1700 Kelvin plus A minus 18.5 times sensible enthalpy of O2 at 1700 Kelvin plus 3.76 times A into sensible enthalpy of N2 at 1700 Kelvin. So, we have to substitute the values. All the values are given in the problem. So, this will be 12 times minus 393.52 plus 73.48 plus 13 times minus 241.83. Please understand enthalpy is in megajoules per kilomole plus 57.76 plus A minus 18.5 times 47.81 plus 3.768 times 45.31. So, now this should be equal to HR, which is given here. So, solving, we will say HP equal to HR implies A will be equal to 42.18. Okay. So, what is the air fuel ratio? So, please understand, for stoichiometric 18.5 A values, A at stoichiometry, remember that will be 18.5, but what we are now giving is 42.18. So, now because you have reduced the temperature, so more nitrogen, more oxygen goes in, so that temperature is reduced. So, now air fuel ratio. (42.18) A into 4.76 into molecular weight of the air 28.84 divided by 170. What is 170? 170 is molecular weight of C12H26. So, this will be equal to 34.06. This is kg air divided by kg fuel. Okay. So, this is the problem. So, in order to reduce the temperature, basically the material aspects have to be satisfied. So, material, if it is subjected to very high temperatures, it will have problems. So, the gas turbine, the temperature is restricted to 1700 Kelvin. For that, excess air is supplied. So, this is about the problem number 6.